Nanostructured plasma coatings are emerging as a revolutionary approach to protecting spacecraft from radiation, extreme temperatures, and space debris. Space is an incredibly harsh environment where materials must endure intense solar radiation, charged particles, cosmic rays, and extreme temperature fluctuations. Traditional protective materials, while effective, have limitations in terms of weight, durability, and adaptability. Nanostructured plasma coatings offer a cutting-edge solution by harnessing nano-engineered thin films and plasma-enhanced deposition techniques to create a new class of space-ready materials. How do these coatings work? Unlike conventional materials that rely on thick shielding layers, nanostructured plasma coatings are ultra-thin films deposited onto surfaces using plasma-enhanced chemical vapor deposition, PCEPD, or plasma-assisted physical vapor deposition, PCD. These coatings contain nanoparticles, nanolayers, or composite structures designed to interact with incoming radiation in a controlled way. Depending on their composition, they can deflect charged particles, absorb harmful UV rays, or neutralize damaging effects of cosmic radiation. Why is radiation protection so crucial? Spacecraft and satellites are constantly bombarded by high-energy radiation from the sun and deep space. Prolonged exposure to solar energetic particles, SEPs, and galactic cosmic rays, GCRs, can cause electronic malfunctions, material degradation, and increased risks for astronauts' health. Traditional shielding solutions such as aluminum and polyethylene offer some protection but add significant weight to spacecraft. Nanostructured plasma coatings, on the other hand, can provide superior protection without adding excessive mass, making them ideal for long-duration missions, including Mars exploration and deep space travel. What makes these coatings effective? The secret lies in their nanostructure, which allows them to manipulate electromagnetic and particle interactions at the atomic level. Some key mechanisms include multi-layered shielding. Alternating nanolayers of different materials can reflect and absorb radiation more efficiently than a single material. Self-healing properties. Some coatings integrate nano-repair mechanisms that allow them to recover from micrometeoroid impacts or radiation damage. Thermal regulation. Certain nano-coatings act as heat shields, reflecting excess heat while maintaining a stable internal temperature. Electromagnetic shielding. Nanostructured films can prevent electrostatic charge buildup, reducing the risk of electrical failures in sensitive spacecraft electronics. How are these coatings tested? Since space conditions are difficult to replicate on Earth, researchers use particle accelerators, plasma chambers, and simulated space environments to evaluate how nanostructured plasma coatings perform under intense radiation and vacuum conditions. Some experiments are conducted on the International Space Station, CIS, where coatings are exposed to real cosmic radiation and extreme thermal cycles. Could these coatings revolutionize space exploration? Absolutely. With the growing interest in human missions to Mars, asteroid mining, and permanent lunar bases, spacecraft must be designed to withstand decades of exposure to space hazards. Nanostructured plasma coatings could enable the development of lighter, more resilient, and self-sustaining spacecraft, reducing the need for frequent maintenance and shielding replacements. What challenges remain? While these coatings show great promise, several questions need to be addressed. How long do they last in deep space environments? Can they withstand extreme solar storms and coronal mass ejections, CMEs? How cost-effective is large-scale manufacturing for missions beyond Earth orbit? Despite these challenges, nanostructured plasma coatings represent a major leap forward in space technology, offering new ways to protect spacecraft and astronauts from the relentless dangers of space. Could this be the key to unlocking long-term human presence beyond Earth? Scientists and engineers are working to find out. The cosmic microwave background, CMB, is the faint afterglow of the Big Bang, representing the oldest observable light in the universe. It is remarkably uniform, with tiny temperature fluctuations that correspond to density variations in the early universe. However, a large, unusually cold region, known as the cold spot, deviates significantly from standard predictions. This anomaly challenges our understanding of cosmic structure formation and raises questions about the fundamental nature of the universe. The cold spot is roughly 70 microkelvins cooler than its surroundings, a significant deviation from expected temperature variations. This is like finding a large frozen lake in the middle of a warm desert. It suggests something unusual happened during formation. The cold spot is about 1 billion light years across, significantly larger than typical temperature fluctuations in the CMB. It is located in the southern hemisphere of the sky, within the constellation Eridanus. If it were a result of normal quantum fluctuations during cosmic inflation, it would be expected to be much smaller. Its size and intensity suggest an extraordinary event or a novel physical phenomenon affecting the early universe. Temperature maps from the Wilkinson Microwave Anisotropy Probe, WMAP, and Planck satellites confirm its existence, ruling out instrumental errors. This is like finding a massive hole in an otherwise uniform quilt, suggesting something disrupted its formation. One leading hypothesis suggests that the cold spot is caused by a gigantic void in the universe, known as a supervoid. A supervoid is a region with significantly lower galaxy density, affecting light traveling through it due to the integrated Sachs-Wolf effect. As cosmic microwave photons pass through the void, they lose energy in an unexpected way, creating an apparent cold region. However, no void large enough to fully explain the cold spot has been conclusively identified. A 900 million light-year wide void has been found in the region, but it accounts for only part of the temperature anomaly. This is like a car losing speed while rolling through a shallow dip, but the dip didn't even explain the full deceleration. Some physicists argue that the cold spot might not be a true anomaly, but rather an extreme statistical fluctuation. In this scenario, the universe's random density variations might have coincidentally produced a cooler region without requiring new physics. However, simulations suggest that such a large and cold area is highly improbable under standard cosmological models, making this explanation controversial. Simulations show that the chance of a cold spot appearing by random fluctuation is less than 1%, but not impossible. This is like rolling a die and getting 10 sixes in a row. Unlikely, but not impossible, in a large enough sample. Another radical idea is that the cold spot is evidence of a collision between our universe and another universe in the multiverse. If parallel universes exist, occasional interactions could leave imprints on the cosmic background radiation. Some theories propose that an early universe bubble collision could create localized temperature anomalies in the CMB, potentially explaining the cold spot. While speculative, this idea is being explored through more detailed CMB studies. Some inflationary multiverse models predict that cosmic collisions could leave large-scale temperature variations in the CMB. This is like seeing a ripple in a calm lake that might have been caused by an unseen object dropping into it. If the cold spot is not explained by standard physics, it could be a sign of unknown fundamental forces or dark energy variations. Some models propose that topological defects, like cosmic strings or domain walls, formed during the early universe could have influenced the CMB. Alternatively, if dark energy is not uniform, it might have caused localized differences in the cosmic expansion, leading to unexpected cold regions. Some studies suggest that anomalies in dark energy distribution could create cold spot-like effects, though evidence remains inconclusive. This is like finding an unexplained gravitational force pulling on objects in an otherwise empty room. Studying the cold spot is challenging because it requires extremely precise temperature measurements of the CMB. Instruments like the Planck satellite have provided high-resolution data, but uncertainties remain. Future surveys, including next-generation cosmic surveys, could help determine whether it is truly anomalous or part of a larger pattern in the universe. If new data reveals similar structures elsewhere, it could indicate a deeper cosmic principle at work. Upcoming surveys like CMBS-4 aim to provide more detailed measurements of the cold spot's shape and structure. This is like zooming in on a blurry satellite image to determine if an unusual object is real or just noise. If the cold spot remains unexplained, it could challenge the LCDM, Lambda Cold Dark Matter model, the current best theory of cosmology. Anomalies like this force scientists to reconsider assumptions about cosmic inflation, the homogeneity of the universe, and even the nature of space-time itself. If confirmed as a new physical phenomenon, it could provide insights into early universe physics, dark energy, or the fundamental structure of the cosmos. Some researchers suggest that the cold spot might hint at new physics beyond general relativity or quantum field theory. This is like finding a missing puzzle piece that doesn't fit with the rest of the picture, suggesting the need for a larger puzzle. If alternative explanations like a multiverse collision or new physics are proven, it could radically alter our understanding of the universe. The cold spot could be the first observable evidence of parallel universes, cosmic defects, or exotic forms of energy. While current observations remain inconclusive, the anomaly continues to fuel theoretical physics, pushing the boundaries of our knowledge. Some cosmologists propose that future missions like the James Webb Space Telescope or gravitational wave detectors could provide indirect confirmation of cold spot phenomena. This is like detecting a faint radio signal from deep space that hints at an unknown civilization, but without yet having proof.